Hi there, my name is Aaron Lanterman. I'm a professor of electrical and computer engineering at Georgia Tech, and in the last lecture of ECE3400 analog electronics, we looked at the equations for a bipolar junction transistor operating in the active mode. Now, the exposition I'm giving you here really assumes that you've seen that lecture, so if you haven't seen that lecture, I would recommend that you go watch that and then come back. In this lecture, we're going to use some derivatives we computed to compute some small signal models for the BJT. In that lecture, we computed derivatives for the collector current and the base current with respect to VCE and VBE, the voltage between the collector and the emitter, and the voltage between the base and the emitter, and we'll use those derivatives to build these small signal models. In this class, we're representing signals using a lowercase letter with uppercase subscripts, and these signals are the sum of DC bias points represented entirely with uppercase letters, plus a small signal variation indicated entirely with lowercase letters. So here we're showing the signal associated with the base to emitter voltage, and we could write something similar for the collector to emitter voltage, the collector current, and the base current, and you could write similar expressions for the emitter current or whatever other quantities you want. So essentially we'll make some Taylor series arguments about the small signal quantities. We'll say that the small signal variation in the base current is equal to the small signal variation in the base to emitter voltage times the slope of the curve that describes how the base current varies with the base to emitter voltage, evaluated at some quiescent operating point, a Q point. And we can write a similar kind of expression associated with how the collector current varies with the base to emitter voltage, but this is a little bit more complicated since the collector current is also a function of the collector to emitter voltage. So we'll write this second term here to deal with that. Now, if you'll recall from the previous lecture, we computed these quantities and gave them various names. So we called the slope of the base current with respect to the base to emitter voltage the input conductance, denoted as G sub pi. The slope of the collector current with respect to the base to emitter voltage is referred to as Gm, the transconductance, and the slope of the collector current with respect to the collector to emitter voltage is referred to as Go, the output conductance. These equations allow us to derive this pi model. So the pi model consists of two resistors and a voltage-controlled current source. So let's focus on the base current here for a moment. We have a relationship that says it's something times a voltage difference, namely the voltage difference between the base and the emitter. So the way this is written, this has the form of Ohm's law in terms of a conductance. So I can express this by putting down a resistor with a given conductance, and by our convention of using G to represent conductances, and the fact that I wrote the word conductance at the top of the slide, we know that G pi is a conductance and not a resistance. Later, I'll flip things upside down and rewrite this in terms of resistances. So what about the collector current? Well, there I have two terms. Here I have a constant times this voltage difference between the collector and the emitter. So I can express that as a resistance with a conductance of G naught. Now, as far as this term here goes, it's a little bit more complicated because I have to deal with the voltage from a different terminal than one associated with this current flow. So here I need to get a little more complicated and use a voltage-controlled current source of Gm times VBE. So that gives me the collector current, and I have these elements in parallel because currents in parallel add. And then for the emitter current, well, that's just the base current plus the collector current. So I implement that equation using Kirchhoff's current law right here in this node. And come to think of it, you could rewrite all of these as current sources, because if you think about what a resistor is, well, you could model what it does as writing down a current source with current given by G pi VBE. So you could replace this resistor with this current source symbol, but that would be extremely confusing. It's just another way to think about what resistors are actually doing in the circuit. So if you look at Marshall Leach's notes on this, he actually gives this current a specific name of IC prime, which lets him express the collector current as the sum of IC prime coming from this current source plus the current flowing through the resistor G naught. And then he'll refer to the current flowing through that resistor as I naught. And then he'll refer to the sum of IC prime and the current flowing through G pi as IE prime. So the actual emitter current is equal to IE prime plus I naught. So he uses these various bits of terminology in various places in his notes. And being able to have a spot to draw this IE prime is why I drew this schematic in this slightly weird way. Now, we're used to thinking about resistors in terms of their resistances, not their conductances. So we'll define R pi as being 1 over G pi and R naught as being 1 over G naught. And then we can just draw this schematic again, but replace all of the G quantities with 1 over the appropriate R quantities. And here, I'm now assuming you realize that by the fact that I'm using the letter R, and R conventionally stands for resistance, and I wrote resistance up here, you know that this R pi represents a resistance and not a conductance. Now, if you go to our previous lecture and look up what R pi and R naught are, we see that R pi is Vt, the thermal voltage, divided by the DC bias current for the base. And then R naught is the early voltage, VA, plus the bias voltage between the collector and the emitter, divided by the bias collector current. The other quantity we need here is this GM, and that's equal to the bias collector current divided by the thermal voltage, VT. I should mention that the way I'm drawing the hybrid pi model here is a little unconventional. Quite often, the collector current is drawn as coming in from the right instead of from the top like this. I like to draw the collector current like this to emphasize the way it matches up with the original BJT symbol. Similarly, they'll often have this current source drawn so that the current arrow is flowing to the left instead of downward. Again, I like to draw it this way to have it match up with the original BJT symbol. Sometimes this R pi will be drawn horizontally instead of vertically. There's all kinds of variations. They're all just different ways of visualizing the same circuit. Now, before we journey onward, I would like to go on a little side quest and talk about beta. So let's compute IC prime over IB. So IC prime is this current arising from this voltage-controlled current source, and it's the part of the collector current that's not flowing through this resistance R naught. So that's GMVBE over IB. And recall that we could write R pi as VBE over IB. This is just rearranging an expression that we had earlier. And so I could replace the VBE over IB with R pi. And now if we recall the expression that we computed for GM, which is just IC over VT, and R pi, which is just VT over IB, if I substitute those into this expression, I see that the VTs gloriously cancel, and I get IC over IB. And now if I imagine the current flowing through the BJT, if I don't have any small signal, i.e. the small signal is 0, I could plug in the DC value for that total current just fine and say that IC over IB is equal to beta. So now notice if I multiply both sides of the equation here by IB, I can write IC prime equals beta times IB. So notice that beta relates the bias collector current to the bias base current, also known as the DC collector current to the DC base current. But it does not, in general, relate the small signal collector current to the small signal base current, also known as the AC collector current and the AC base current, although I'm not hugely fond of that particular terminology. It does relate IC prime to IB, so I thought that was kind of interesting. Now, it does directly relate these quantities down here, these small signal quantities, if R naught is infinite, because then we can essentially take this out of the circuit and IC equals IC prime. So that's the hybrid pi model. There's another model that comes in handy sometimes called the T model. To derive that, I would first like to derive a few other relationships between these various quantities we have on this pi model schematic. And these relationships are often useful in their own right beyond just deriving the T model. So let's talk about those. So this IE prime, that's equal to IB plus IC prime. So it leaves out this I dot portion. Now, IC prime equals beta times IB. That's something we just figured out on the previous slide. So I can divide both sides of this expression by beta and replace the IB here with IC prime over beta. So let's just write that as 1 over beta plus 1 times IC prime. And let's rewrite the expression in the parentheses here as 1 plus beta over beta. And recall that we defined this alpha quantity previously that's beta over 1 plus beta. So I can say that IE prime is equal to IC prime divided by alpha, or IC prime equals alpha IE prime. So alpha here is relating a small signal emitter current to a small signal collector current, but not the full small signal collector current and the full small signal emitter current. It's instead relating this IC prime to this IE prime. So this alpha is not including I naught in its considerations. Now, let me take this IC prime equals beta IB expression up here and plug that in for IC prime, because then I can write beta IB is equal to alpha IE prime. And now I get this relationship that IB is equal to IE prime times alpha divided by beta. So I now have an expression relating the current here to the current here. Now let me take this expression here and copy it on the next slide up here. And now we can talk about deriving the T model. And I'll be straight up with you, I find the T model really weird. I have a hard time wrapping my head around it. It's often useful in terms of solving particular circuit problems, but I don't really actually have a good intuition on it. The hybrid pi model drops out directly from the equations that we derived earlier, but the T model feels more like a trick. So in the T model, we get rid of this R pi, and instead we place a resistor here in this IE prime slot. And what we're going to do is we're going to choose this resistance RE so that IE prime on the right here matches the IE prime that you get on the left. So we're basically making up this resistor RE out of mind matter. So when we analyze the circuit using our rules of circuit analysis, we wind up with the same overall effect from the outside as the results we get from the hybrid pi model. But in a way, this isn't too weird because although this resistor RE isn't quote-unquote physical, well, this resistor R naught and this resistor R pi, those aren't real resistors either. They're all just things we made up to fit the math. So here's the idea. What we would like to do is to match the VBE on the left to the VBE on the right. So VBE on the left, we could write with Ohm's law as IB times R pi. And for VBE on the right, let's write that as IE prime times RE. All right, so let's replace this IB with this expression we computed on the previous slide. Since then we wind up with IE prime on both sides, and we can cancel those out, and then we can write RE is equal to alpha over beta R pi. So now we have a relationship between R pi and RE. So let's take this expression, rewrite it on the next slide, and then remembering that R pi is equal to VT over IB, we can write this as alpha VT over beta IB. And remember, beta IB itself is just IC. And remember, IC over alpha is IE. So we have several different ways of expressing RE depending on what is most convenient. Notice that RE and R pi are very similar. Basically, the only difference between them is that R pi uses the DC base current and RE uses the DC emitter current. So that was a lot of formulas, and there's more formulas coming. If you go to Marshall's website and go to his ECE3050 page, 3050 is an older number for what's now called ECE3400, And if you scroll down a little bit, you'll find this BJT formula summary sheet. So most of this we'll actually talk about next week. But if we scroll down a little bit, you'll find a whole bunch of formulas, including these relationships between IB and IC and beta and alpha, and formulas for GM and RPi and RE and R naught. The rest of this we'll talk about later. Well, some of this we'll talk about later, and some of it I'll just kind of hand wave about. We'll mostly be using the approximations down here, but all of that is going to come later. So to compute these small signal quantities, we need to know what the various bias quantities are. So that is what we're going to talk about next time.